This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's problem is to evaluate 13 times e to the 1 minus a half plus a third minus a quarter, etc. The first method is to simply recognise that the natural logarithm of 2 is equal to 1 minus a half plus a third minus a quarter, etc. In which case, this is equal to 13e to the natural logarithm of 2, e and log cancel to give 13 times 2, which gives us 26. The rest of this video quickly examines why this is true, and if we didn't immediately recognise it, how could we try to deduce it? It is tempting to justify that the series equals the logarithm of 2 from the Taylor series expansion here. Indeed, if we substitute x is equal to 1 into this expression, we get that the logarithm of 2 is equal to 1 minus a half plus a third minus a quarter, etc. The problem with this, though, is that a Taylor series has got a region of convergence. In this case, the region of convergence is the absolute value of x needs to be less than 1. Here, the absolute value of x is equal to 1. It's on the boundary. If x were larger than 1 or smaller than -1, then the series on the right-hand side would diverge. It would not converge. If x equals 1, then it's a boundary case. This means further effort is required to prove that the right-hand side actually converges when x is equal to 1. Indeed, it can be shown that the right-hand side does not converge when x equals -1. The series 1 minus a half plus a third minus a quarter, etc. is an alternating series because successive terms alternate between being positive and negative. Moreover, the absolute value of each term decreases to 0. It's a well-known result that any such alternating series whose terms, when taking the absolute value, monotonically converge to 0 will itself be a convergent series. Therefore, when x is equal to 1, the right-hand side is a convergent series. It's on the boundary of the region of convergence, and therefore it equals its left-hand side. That it equals its left-hand side when x equals to 1 is a non-trivial result. It's based on Abel's theorem, which tells us that if a power series converges at a particular point on its boundary, then its value there is given by continuity. We can take a sequence of points inside the radius of converging to that particular boundary point, and take the limit, and we get the same answer as to what this series converges to. And on the left-hand side, the logarithm of 1 plus x is a continuous function about x equals to 1. So by continuity then, we have the left-hand side equals the right-hand side at x equals 1. What if we did not think of the logarithm function when trying to evaluate this series? Well, in general, there is no set rule for evaluating a series, so one can ask, what is one more likely to know? The Taylor series for the log and recognise this, or the following trick? Nevertheless, we present the following trick for completeness. The first step is to actually make this into a Taylor series by introducing a variable x. Thus, we think about x minus a half x squared plus a third x cubed minus a quarter x to the power of fourth, and so forth. Denote this series by s, and consider what we get if we differentiate s term by term. Derivative of x is 1. Derivative of a half x squared is just x. Derivative of a third x cubed is just x squared. Derivative of a quarter x to the fourth is just x cubed, and so forth. The reason we thought to differentiate was because we noticed that the coefficient here would get cancelled by the power when we differentiate, so we get an easier sequence to work with. The one series, which we should all know because it occurs so often, is that 1 minus 1 on x is equal to 1 plus x squared, etc. This implies that this is equal to 1 on 1 plus x. Nevertheless, if we had forgotten this, we can also derive it as follows. I've already used s, so let t be equal to 1 minus x plus x squared minus etc. Then x times t is equal to x minus x squared plus x cubed, etc. If we add these two together, we get 1 plus x times t is equal to 1. Then that cancels, and because they both go on forever, all the other terms cancel, so therefore we just get that t equals 1 on 1 plus x. Technically, we still have the problem that we need to know that our series converges. What we found here, if you like, is the analytic continuation of this series for values of x that might make this original series diverge. Nevertheless, we can show that what we're doing here is certainly true if the absolute value of x is less than 1, and earlier we showed that this particular alternating sequence converged. If the derivative of s is equal to 1 on 1 plus x, then s itself must be equal to the integral of 1 on 1 plus x dx plus an appropriate constant of integration. Integrals are a bit like series in that you need to have some background knowledge in order to try to figure out what they are. In this particular case, we should be able to recognize that this integral is given by the logarithm of 1 plus x plus the normalizing constant. To figure out the normalizing constant, we simply need to take a particular value of x, the simplest being x equals to 0. When x is 0, our sum is clearly 0, and the logarithm of 1 plus x when x is 0 is the logarithm of 1, which is 0, so in fact this is equal to this, with the normalizing constant equaling 0. In this way we can go backwards, and starting with this alternating series here, we can deduce that it's related to the logarithm of 1 plus x in some way. Precisely, the logarithm of 1 plus x is equal to this series, and when we set x is equal to 1, we recover this series here.